Hello, Mr. Siegel. This is video part installation 3, the third of 4 problems, and I guess let's just get started. A mass M slides down a frictionless incline that has an angle theta with respect to the horizontal. Okay, so what hits me initially is that we need a drawing and a force body diagram. So looking at the drawing, we see a block of mass M go down the length L of a incline and which has an angle theta. Now, looking at the force body diagram, we see the normal force, which, unlike on a flat surface, would be straight up. It is at an angle, which represents the force of uh, that the incline has on the block. Now, looking at the gravitational force, that remains straight down because the gravitational force never changes direction. However, we are left with a gravitational force perpendicular and a gravitational force parallel. The perpendicular gravitational force is the force of the block going down on the incline, and the gravitational force parallel, well, that is what's forcing the block to move. That is actually the net force that allows the block to go down the incline. So, in terms of m theta and any applicable constants like g, let's calculate the amount of the mass's acceleration. So, we must apply Newton's second law. What is Newton's second law? Funny you ask me. Known as F equals mass times acceleration. In our physics class, we like to represent it with acceleration equals the net forces over mass. So, in this problem, the only net force acting on the object, because there is no friction, as we saw earlier, because it is a frictionless incline, and on top of that, because the Fg is straight down while the block is moving at a not completely vertical direction, but rather down an incline. So we see that the only force acting upon the object and the force that is causing it to move is Fg parallel. Well, what is Fg parallel really? Looking at it, where our theta was, so back to the force body diagram, just move it up here. Back to the force body diagram, you can see that the theta is where the angle is, and we can see that Fg is the hypotenuse of the so-called triangle between Fg parallel, Fg perpendicular, and Fg. So we can solve using trigonometrics, which is sine, cosine, tangent. So we have Fg parallel is equal to Fg, which we have here, and then we can see that the theta represents this angle. So it's really just going to be the opposite over the hypotenuse. Well, what's opposite over hypotenuse? That's sine. So we have Fg times sine theta. Well, what is Fg? Because remember, we can only represent this in constants. Fg is really just a mass times the acceleration due to gravity. So we have Fg parallel is equal to m times g times sine theta. So we know what Fg parallel is. Now we can solve for acceleration. Acceleration is m times g times sine theta over m. Those easily cancel out, and we're left with an acceleration that is equal to g sine theta. Okay, so if the mass starts at rest, calculate how much time the mass takes to slide a length L down the incline. Use kinematics. That's the way we're going to solve this, of course. So a trick that students might run into, not just where to put theta, but also looking at specifically how we solve this problem, because it's very easy to say delta x equals v1t. That's something we've been taught. However, remember that delta x equals v1 times t only works when the acceleration is 0, meaning that the velocity is constant the whole way throughout. This block does not have constant velocity due to the acceleration due to gravity. So we cannot say that the block that we cannot say that x equals v1 times t. That is an incorrect statement. However, we can use our kinematic equations that we learned throughout the year using an amazing mnemonic song that we were taught. Specifically in this one, we can use delta x equals v1 times t plus 1 half a times t squared. What variables do we have? Good question. So we already solved for a, as we saw in 1a. Our acceleration is equal to g sine theta. Our initial velocity is 0 because it starts at rest. Our x is the length L, and we're solving for time. So again, we have our x variable, solving for t, and we have a. And of course, we can cancel this out because v1, if v1 equals 0, then this whole entire, no matter what t is, this entire term is going to equal 0. So solving for terms of t, we can come out to find that t is equal to the square root of 2L over g sine theta. So we talked about something you could mess up in B, but let's go back to A quickly and talk about something that students might very easily mess up there. Looking at A, a very simple yet tricky thing that students can mess up is realizing that because the slope is frictionless, that perpendicular, FG perpendicular has no effect on any, no relevancy to acceleration because there is no friction. If there was friction, we would have to use this as one of the sum of forces in our equation. However, because there's no friction, Fg is the only force that acts upon the object. And remember that theta is always the angle. Theta always goes closest to the angle closest to where the dot is on the force body diagram. So it's not going to go here, which is a mistake that a lot of students make. Theta is going to stay close to the dot. That's just how I remember it, and I think that's an easy way for other students to remember it. So thanks again. This is problem number 3. Problem number 4 is on the way, and we're about to finish it out. So let's go.